Okay, so welcome everyone. So today we are going to discuss about testability of RF circuits. So this short course is supposed to be just an introduction. Introduction meaning we would learn what are the things that are important for testability of RF circuits in particular, and later on I'll probably toward the end of the course, which is about 1.5 hours, I will show what are the current challenges on which we can do our research. So basically, from student standpoint, when we are done with this short course, we would have at least some amount of idea if someone is building a career for RF circuit design and testability, what are the things that one may encounter in future. So with that introduction, I go to the outline of the course. So the outline is circuit design to manufacturing of ICs. What we are going to do in this particular bullet is that I'm going to give an overview from circuit design to the circuit manufacturing, and we'll go through each step and we'll show what are things that are important and what are the things that are useful or that are care about for testability. Next, I'll discuss the design characterization and production tests, particularly the difference between them. In the next bullet, what I'm going to discuss is the circuit specifications for RF circuitry. There are a lot of specifications that one would encounter for RF circuits. So some of the RF circuit specifications, I'm going to go over them and describe what they are. And at the very end, I'm going to discuss the design for testability aspect of the RF circuitry, and I'll show what are the things that are currently going on in terms of research. I mean university research. Okay, so that is primarily the outline. So first we take on the design, circuit design to manufacturing of circuits and systems. So you see that there are 3 blocks, and the first block on the very left hand side is the CAD and simulation environment, and the second block is the post fabrication block, where we try to characterize the design prototype, and the third block is the production test environment, which is used for volume testing of the circuit you have designed. So in the left hand side, what we start with is the specifications and the technology library. For example, I am designing an amplifier. What are the things that are important? Probably I am given a certain gain specification, certain frequency response specifications. So these are basically the circuit specifications. And for RF circuitry, it is not only the gain and frequency response you will be dealing with. There are a lot of other things to consider, like input impedance, output impedance, power consumption, noise performance, so on and so forth. So these are the circuit specification you will be given with when you start the circuit design. And another ingredient that you will be using when we are in CAD and simulation environment is a technology library. For example, you are designing a circuitry and you are using, say, for example, National Semiconductor's fabrication facility to realize your amplifier design. So in that case, you need the technology library which corresponds to the process that National Semiconductor uses for that particular technology node. For that particular technology node, meaning the VCC it uses, the channel length it uses, so on and so forth. Suppose you are using, say, some other foundry, say TSMC. In that case, you need the technology library corresponding to the TSMC fabrication process or TSMC foundry. So these two are the things that you would be given when you start your designing of RF circuitry or any other circuitry. So using these, you design, and as long as you are within simulation environment, you simulate, re-simulate, simulate over again to make sure that whatever gain specification or whatever frequency specification or noise performance specification that you are given with in the beginning, you meet them, okay, for the given technology library. Okay. If we do not meet them, it is no point to fabricate that circuitry. Okay. So once we make sure that design is verified within the CAD environment, we go for prototype fabrication. So if we are using, say, for example, National Semiconductor Design Library or Technology Library, we are going for circuit fabrication in the National Semiconductors Foundry. So we get the prototype, say several ICs, maybe 25 ICs or 100 ICs. It depends on how many you want. So you get the prototypes. Now the question is, whatever you verified in the simulation environment, basically those circuit specifications, question is, do they hold good after you have got the physical ICs back in your hand? So you have to do the design prototype verification on board, okay? On board meaning on PCB. So you have to fabricate some sort of test fixture on which you can mount your prototype IC so that you can connect the IC from, say, you can connect the IC to the test signal generator, for example, say function generator. You can connect the IC to the oscilloscope so that you can see the response waveform. So you have the test fixture, you apply the test signal, you measure the test response, and you try to do the design prototype verification. That brings us to the next thing, the characterization and reliability testing. Just verifying some of the specification is not good enough. You have to verify the specification over the VCC, over the temperature, over all the process corners. Then only you are done with the characterization. Okay. Then once you are satisfied with all the specifications being within the target that you started with here, over here, basically follow the mouse pointer over here, only then you go for volume production. If it doesn't meet the target specification, there is no point going for the volume production. You have to go back in the CAD environment, fix the problems, and again do the prototype verification. Okay. So suppose my specifications that I started with are all met. So I go for volume production. So now I'm not dealing with maybe 50 devices or 100 devices. I'm dealing with hundreds of devices or thousands of devices depending on the application. Okay. So in volume production, the key criteria is that we are talking about testing of thousands or maybe millions of devices. Okay. So we have to automate the test capability or testability approach so that we can test the specifications against the specification that we started with easily and cost effectively, right? It is no point going through each and every device for maybe million devices for hand testing. We have to automate. So in case of production testing, there are two levels of production testing. One is the wafer level production testing, and second is the package device production testing. So when you fabricate your IC, they come in wafer. So basically each wafer will be containing thousands of devices depending on the die size, and you use the so-called equipment wafer prober to touch down on the wafers, particular devices, to excite the device with particular test stimulus. You observe the test response, you calculate the specification, make sure the specification is meeting the specification you started with. Okay. And the second level of testing is the packaged testing or assembled package testing. Sometimes it is called the final testing because that is the very final test that you do before shipping out the devices to the customer. Okay. So these are the two levels of testing. Now after this testing is of wafer level and final test are done, you integrate the system and you do the system level production testing. Okay, so depending on whether the semiconductor provider or the technology provider is providing just bunch of ICs or providing the integrated system, you break the process over here to ship the ICs, or you break the process after you are done with the system level integration and system level testing and break the process down here. Okay, then you send it to the customer. So these are the main steps, starting from the conception of the design, going to the volume manufacturing and testing, and shipping of the ICs or the systems to the customer. Okay. Now the question is, why do we need to test at all? For example, suppose I started with the specification over here and I made sure that it meets the specification. I characterized it over VCC and temperature. I made sure that it is passing my specification or meeting my specification. Then why can't we just fabricate for millions of devices and done with it, no test? The thing is, there are two things that happen in manufacturing. The first type of thing, or the first type of problem, is the catastrophic fault or defects, manufacturing defects. And the second type of thing is so-called the process variation, process parameter variation. In the first thing, here I am showing two examples actually. In the left hand side, you see that if the circuit was proper, or if the circuit was properly fabricated, in that case you would not see this blob in the circuitry. There is some dust particle or dirt particle that fell on the die during the process. So there are thousands of ICs, maybe say 2000 ICs on a single wafer. So out of 2000 ICs, one IC has got this dirt particle, and somehow it is shorting this line and that line. In that case, you have got a short circuit problem, right? So this circuit is most likely not going to meet the specification because you have some circuit node shorted with some other node. Okay, so this circuit is not going to work. So although we made sure that characterization, I mean my overall device is passing the characterization, but this particular individual IC is not going to meet the specification, so we have to test for it. Similarly here, we are showing an example where the via on some upper layer is not touching down completely onto the lower layer. So this is one metal layer, this is another metal layer. If the circuit fabrication was done perfectly well, we would have got a proper connection over here. So here is a open circuit problem. Okay, so these are the defects. Similarly, other than the defects, we have problems of process parameter variation. So when we talk about, say, fabricating a circuitry using, say, transistor, maybe BJT or maybe MOS, there are process parameters like oxide thickness, doping density, which would vary from one wafer to another wafer. So for example, the gain that you started with in the first place may not be the same gain that you get when you are testing for the second wafer or testing the devices from the second wafer. So the gain value will have a variation. So basically the performance specification will have a variation when we go from one wafer to the another. So we have to test for it. Okay. So here we set up the criteria, or we discuss the criteria that are paramount for characterization tests. Okay, so there are two types of characterization that are possible. One is on wafer IC characterization, which you can do on bench or in the bench environment using the wafer probe station. Okay, or you can do in the production environment using the wafer prober. Okay, and the second type of characterization is possible, which uses the packaged IC characterization, which uses the part to solder down on PCB or putting it on a socket onto the PCB and testing it on the bench environment. You can do the same characterization in the ATE also, where Instead of a say regular PCB, you will have a special PCB or standardized PCB called device interface board or DIB to do the characterization. Okay, so the basic criteria is that you need a measurement fixture. Okay, you need measurement instrumentation, obviously. For example, you need function generator or RF signal source as the test stimulus generator. You need measurement capture instrumentation or test response capture instrumentation like say spectrum analyzer or oscilloscope, okay, to capture the measurement and calculate the specification. So you need measurement instrumentation apart from the measurement fixture, okay. And the purpose of the characterization, device characterization, is to measure all the specifications over all the process corners. All the process corners meaning over the VCC range, over the frequency range as in suppose the particular amplifier that I am designing is operating from 1 gigahertz to 1.5 gigahertz. We have to make sure the gain that you targeted at 1 gigahertz, you are getting it. That gain you targeted at 1.5 gigahertz, you are also getting it. So we have to meet the frequency range, and that particular gain specification has to meet for the particular VCC. For example, the device is using say 3.3 volt VCC, for example. So there will be a certain range of the VCC. For example, say it is 3.1 volt to 3.5 volt. So you have to make sure that you are getting the particular gain that you targeted for at 3.1 volt as well as 3.5 volt. You have to cover all the process corners. Not only that, for RF circuitry, we have to cover for the load variation. For example, if the amplifier is specified for 50 ohm, okay, if the specification, if the load varies from 55 ohm to 45 ohm, will the gain distort or change drastically, or does it stay almost close to the typical value? So you have to measure the gain specification for the load variation as well. Okay. Similarly, if the product or if the amplifier is specified for say minus 40 degree to 85 degree centigrade, which is industrial grade temperature range, you have to measure the gain specification for all the VCC, all the frequency range, as well as all the temperature like minus 40 to 85. Okay, and not only that, you have to do this characterization over multiple wafer lots. Why? Because the process parameters are going to vary from one wafer lot to another. Okay, so these are the main things that are there for characterization. There are additional things as well. You have to qualify that particular amplifier you designed or any other RF circuitry that you design over the, for the electromagnetic interference and electromagnetic compatibility like EMI, EMC. You have to qualify the amplifier for ESD, electrostatic discharge, immunity. You have to qualify the IC for package thermal characteristics. Particularly, I said that minus 40 degree to 85 degree centigrade, say this is the specification. You have to make sure that there is no thermal runaway. Thermal runaway meaning no part within the IC, no junction within the IC is running not so hot that it is going to a melting situation. So basically, you have to qualify for the thermal specification as well. So other than that, we have to qualify the IC, say the amplifier, for real life application. You see that when you are talking about characterization of particular amplifier, putting it on the PCB and say connecting it to the RF signal source and RF spectrum analyzer, we are not putting the circuitry in real life scenario. In real life scenario, probably some other circuitry is driving that low noise amplifier or just the power amplifier. Okay, so we have to put that IC, integrate with real life application, and make sure that it is running properly. So that is also part of the device characterization. Okay. And there is also one other point that I have mentioned here, which is also part of the characterization, is that you see in characterization, you can put a dedicated power supply to power up your amplifier or mixer, RF mixer, whatever you are designing, right? But in real life application, that power supply, dedicated power supply may not be there. It would be sharing the power supply from the entire system. So in that case, there may be noise related issues, noise getting contaminated from the other portion of the circuitry in the system to the circuitry that you are designing. Okay, so sharing of the resources like power supply and the ground plane, that you have to also qualify for during the characterization. Okay, so these are the main things in device characterization. So I'm giving here one example here, and what I've done is I've taken a PLL VCO synthesizer from one particular vendor, National Semiconductor. It is LMX 040000 series signal generator, RF signal generator. Okay, and I just took the particular portion, the frequency range, and the output power, RF output power, that specification. You see that it is a family of devices. The specification varies, for example, say LMX 40X3, 1840 megahertz to 2160 megahertz. So it's going all the way up to 2.16 gigahertz. And corresponding power specification, RF power specification, you see that it's varying from 0 dBm to -5 dBm. So when it is operating at 1840 megahertz, it's giving out 0 dBm output power, RF output power. And when we are operating the PLL VCO synthesizer at 2.16 gigahertz, it is giving out -5 dBm output power. So during the characterization process, you have to test over the frequency range, over the VCC, over the power levels, so on and so forth. So to do that, you'll be probably using some kind of PCB fixture like this. Here what I'm showing at the center is the soldered down part. So this is really the device under test or design under test that you have got after prototype fabrication. So you're putting it down, soldering it down to the PCB. Other option is that you use a test socket, also called the contactor, on the PCB, and you use the part, you place the part within the contactor. The advantage of using the contactor is that unlike in soldered down PCB, you can take the part out and put another dot. You can, after you are done with the testing, you take the part out once again, put say third part, so on and so forth. But in case of soldered down PCB, as many part you are characterization for, as many test fixture you should have. Okay, so there is a cost issue. But the thing is, there is performance issue as well. So if you are using contactor, in that case, the inductance and the parasitic capacitance of the contactor or the socket, that will come into play. That may change or that may degrade the circuit specification, for example, the RF output power level that we discussed a little bit, and which the real life application may not see at all. Okay, so using contactor, you may come up with value that are not true in real life application. Okay, so the best possible case or best possible scenario is to use the soldered down part on the PCB fixture and do the characterization, but it comes at a price. Okay, so here if the recommended operating condition is saying that I have to qualify the product from -40 to 85 degrees centigrade, I have to do all the tests from -40 to 85 degrees centigrade. If the product specification for VCC is 3.15 to 3.45, I have to do the test for the VCC range as well. Now, when you go for production test, we do not test for all the corners. All the corners meaning we do not test for all the temperature range. We do not test for all the VCCs. We test for only the worst case scenario. Okay. So for example, if the 85 degrees centigrade is the worst case scenario, we have to create a test condition in production test so that we can test the part at 85 degrees centigrade. If creating the 85 degrees centigrade scenario is a problem, in that case, we have to characterize upfront what is the performance shift, say the RF output power level shift, when we go from 25 degrees centigrade to 85 degrees centigrade, and when we calculate the specification in production test, we have to subtract that shift amount so that we make sure that whatever RF output power specification you measured at say room temperature is meeting the particular specification we started with. Okay. So the main thing is the volume or the number of devices that we test is much larger than what we use in characterization. Okay. And there is also another market difference from the characterization test is that we have a pass and fail criteria, meaning pass meaning whether the circuit meets the specification, fail meaning whether the circuit doesn't meet the specification. If the circuit doesn't meet the specification, we have to throw away that part. We cannot, as a semiconductor technology provider or semiconductor vendor, we cannot ship out a part which does not meet the target specification to the customer. Okay. So there is a decision making criteria, good versus faulty, and in selected cases there are decision making criteria also for fault grading or performance grading. Okay. For example, say I have a RF signal generator or RF signal synthesizer, an IC, RFIC basically. It is supposed to run all the way up to 2.1 gigahertz. Now suppose it runs up to 2 gigahertz, it doesn't go all the way up to 2.1 gigahertz. Going by the first criteria, good versus faulty, I throw away that particular device and I do not ship them. So I scrap that particular device. Okay. But the other possibility is that, well, I say that it is not it is not the device which meets the specification perfectly, but it is somewhat inferior. So I call it a grade B device. Okay. So this kind of juggling with the specifications and performance grading, you are probably familiar with. For example, say Intel processors, there are speed grades, right? Some processors are not meeting say 3.2 gigahertz, it's probably meeting say 2.4 gigahertz. So they are selling it at a reduced price at a lower performance grade. Okay. So that concept comes from this thing, performance grading by binning. Okay. There is another thing called guard banding. Okay. So the idea of guard banding comes from the fact that whatever we measure, say if you are running an experiment in the lab, say you have created an amplifier on the breadboard and measuring the gain specification. Can you say every time you measure you get the gain number value or particularly gain value say accurate to the last 3 digits? No, right? There is a distribution. Okay. So we are talking about a tolerance. You do the same experiment today, you done the experiment say 1 week later, you may not get the same value. So there is a tolerance. So the idea of guard banding is that we have to make sure the circuit specification, for example, the gain specification that we measure is within the target, but there is an uncertainty or tolerance. So we have to tighten the acceptance criteria or make the acceptance criteria a little more stringent so that we always make sure that even there is a tolerance in the measurement system, we are never going to ship out any doubtful or questionable part in terms of that particular specification to the vendor. So let us give an example. So here I have say 0 dBm, and let's say uncertainty is about 0.2 dBm. Now if my acceptance criteria is 1 dBm, and in the production test I measure a actually RF output performance specification to be 0.9 dBm, we know that there is plus minus 0.2 dBm uncertainty. So we really cannot use the 1 dBm as the acceptance criteria. We have to tighten it, we have to make it more stringent by the tolerance amount. So if the target specification is 1 dBm, we set the acceptance criteria 1 minus 0.2 dBm and set it to 0.8 dBm, so that we make sure that 0.9 dBm specification that we measured is going to, that particular device is going to get rejected because there is some uncertainty. It's a questionable performance device. Okay. And there are other additional things, like I mentioned, there is high level of automation. The test stimulus, for example, you are hooking up RF signal generator from the test equipment. That hooking up is automated. You are hooking up, say, spectrum analyzer. That connectivity, that making of that connection and breaking up that connection, that is also automated. Data analysis has to be automated. Pass-fail decision making, like I gave the example, you are comparing the RF output pass specification with respect to a certain 1 dBm acceptance criteria. That has to be automated. Okay, and there may not be just one gain specification or RF output pass specification. There will be multiple specifications. So there is a question of sequencing the tests, meaning which test I'll do first, which test I'll do later on. So that portion has to be automated too. Okay. And last but not the least, the mechanical handling of the devices before the test and after the test. Before the test, you start with, say, a tray of devices. You don't know whether the devices are going to meet the specification or not. After the test, you know. So after the test, you have to sort out the good devices and segregate it away from the bad devices. So there is a question of mechanical handling or sorting. So that has to be automated too. So we use wafer prober and the handler in production test to do that job, mechanical handling job. So apart from these, there are a few additional criteria, like in production tests, we'd like to do those tests first, as soon as possible, which are prone to failure the most, which are likely to fail the most. For example, suppose I have the gain specification as well as the output power specification, okay, and RF output power specification is supposed to fail the it's most likely to fail. In that case, I would like to test the RF output power specification first or before the gain specification testing, because in that case I save the test time. So whenever we are talking about testing of, say, 1,000 devices, if I see that 80% of devices are failing the RF output power test, I save the time for those 80% of devices by doing the RF output power test earlier. So there is a test sequencing problem here. So that is also a research problem, by the way. There are quite a few papers how to effectively sequence the test based on the percentage of failure or most likelihood of failure, and number of devices that you have to test, and the test time that each test will encounter. Okay. So all of these, the objective of all of this finally comes down to the fact that you have to screen out bad devices from good devices so that you don't ship questionable part or bad part to the customer. Okay. So here using the next few slides, I'm going to show what exactly is done in terms of production test to test the ICs in volume. Okay, so there are two kinds of approach. The first one is using the singularized devices, meaning you have say a packaged part like this. So the white marks that you are seeing here are basically the package pin. This is so-called the LLP package or lidless frame package, where there is no lid. All of them are underneath the package itself. So you can test one by one. If you test one by one, then the mechanical handling becomes a tougher problem. So what they do in manufacturing is that they create a strip like this. So this is called strip testing, and each of the dots that you are seeing here is a IC, is an IC here. So what one will do, actually it's not shown here, what one will do is that instead of feeding one IC at a time, you will feed the entire strip within the package tester or final tester or so-called the handler, and you will test the entire thing at a time. So basically what actually I'll come to that later on. It will be clearer when I show that. Here I am showing one example of the AT test fixture. So like I mentioned, for characterization test or characterization data collection, you need a PCB, right? Usually it is square shape that we are familiar with, but depending on the particular test platform, the shape of the PCB that is used in the production test, that can vary. Okay, so here we are showing the PCB, which is basically the device interface board or DIB for a particular test platform called Teradyne Catalyst. Teradyne is a vendor name, and Catalyst is the test platform, and DIB is the device interface board. By the way, these are the references. At the end of the presentation, I have provided the references. So if you are likely, if you would like to do further study, you can always look at that. So the parameters that are standardized is the size of the PCB, thickness of the PCB, the location of the connectors. You see all the dots that are here are locations for connectors. So whenever you are using the PCB within the tester, you are basically touching down on these exposed gold plated sections where you are making the electrical contacts. Okay, and this is the contactor or the socket. Okay, so in the center you are going to put the contactor or the socket. Okay, and you see that in the there is a groove at the center. In between you put the IC that you are going to test or make a measurement of. Okay, after you have put the IC, you place the actuator on top of it so that it doesn't fall away or something, and you are making a good electrical contact from the underneath of the PCB, basically all the electrical contacts via the contactor to the package pins. Okay, so you are putting this device here, putting the actuator, making sure that it forms a good contact from the package pin to the contactor, and this contactor is placed onto the test fixture or the device interface board. It makes a good contact to the circuit electronics that you may have on the test fixture, and finally all the way to the test instrumentation, which is also making contact to these predetermined locations of gold plated touchdown area. Okay. And here, so basically we are kind of going bottom up meaning we are taking a device, then taking the strip, then going to the device interface board, and finally we are showing the tester or actual automated test equipment or ATE that is used in the production test. Okay. So here on the left hand side is a picture of an ATE. I mentioned the name earlier, Catalyst RF from Teradyne. Okay. This is rather, I mean, considering it is 2009, it's rather an older tester technology. When it was introduced, it used to cost about $2 million. The reason it is so costly is that so much of flexibility is provided within the tester itself. If you have to test all the specifications in a sequence in a bench environment, it is hugely cumbersome to do that and to automate it. The main cost, or I mean the thing that makes it costly is particularly the automation aspect of the test. Okay. So here it is a block diagram of the same thing that we show on the left hand side. It has main two parts, actually three. One is I'm not showing, I'll tell you later. The first part is the mainframe where all the big instrumentations are located. For example, you are testing an RF specification of RF output power at say 1.5 gigahertz. So there would be a signal generator, RF signal generator sitting within the mainframe. Okay. And suppose you want to capture the test response at 1.5 gigahertz. So there will be an spectrum analyzer sitting within the mainframe. Okay. And it sends the signal, the test signal generator will send the signal through this bunch of cables. Okay. And it will go to the test head. So this is the second part or second section of the AT, is the test head. Okay. So actually in the next slide I'm going to show the detail of it. And on the test head you place your device interface board, on which meaning on the device interface board you place your device to test. Okay. So the test response comes out of the device, goes to the test fixture, comes out of the test head, goes to the ATE, and where you do the analysis. So the first part is the mainframe, second part is the test head, and the third part which is not shown in this diagram is the test control or the host workstation, which is like regular Sun terminal or something like that to load the test program and run your test program and do all kind of analysis, data analysis. Okay. So this is really the third part I was talking about. So here it is a closer look of the test head. Here you see that this is really the section which provides the mechanical stability of the whole frame. This entire thing is movable in three directions, X, Y, Z. You can rotate it, twist it, put in every direction actually. It's rather fun to see if you get a chance to see one. In this particular configuration, it is shown, the test head is shown to be upside down. Okay. So actually the device interface board will be sitting at the bottom of it. Okay. And if you are doing strip testing, meaning you are putting bunch of devices on strip, there will be a strip handler which will be connected from the bottom. So the test head is upside down, you are connecting the strip handler and you will be running your battery of tests or sequence of tests, one device after another. You run it for thousands or tens of thousands depending on what is the capacity of the strip test handler. Okay. So this is really the side view, and this is again the front view showing the test head. So this is showing the overview of the steps that you would do. You fix the socket or the contactor on the device interface board first. Okay, so basically you are putting the socket on the PCB meant for production testing. Okay, then you place the device interface board on the AT test head. Load your test program, which will run the sequence of tests in the AT workstation. The fourth part is an one-time task, but it's crucial for before making any tests. Is a calibration of all the equipments that you are going to use for testing. Suppose you are doing, say, RF output power measurement, right? So in that case, your spectrum analyzer built in within the mainframe has to be calibrated before we run the sequence of tests. Okay. Next is the place the device to be tested in the contactor, like I showed earlier here. Okay, and manually put the actuator. If you are doing the production test over multiple devices, you don't put the manual actuator. Actually, the handler has got an arrangement to press the device snugly onto the test fixture, actually the test contactor, so that you have a good electrical contact from the device interface board to the PCB. So there is no manual actuator in case of production testing. The handler is doing it for you, basically the mechanical handler which is doing the automation of the sorting of the devices. Then you run the tests. Okay, so you are applying a series of test stimulus, capturing the waveform, and using the test stimulus waveform and the test response capture waveform, taking them together. You're calculating the test specification, for example, gain, output by input. You do it over multiple frequencies, right? So you calculate one when you are measuring output power. There is no really any RF input. You're just measuring the output power itself. So you're just making use of the spectrum analyzer only, the test response capture portion only. So you do all series of test stimulus application and test response measurement and subsequent calculation of the test specification. Okay. Now, for each test, you determine whether your circuitry is meeting the specification, whether the gain or the RF output power or not. Okay, right. So if it doesn't meet the specification, you break the process and declare that, well, the circuit is faulty, I want to go to the next device. Okay, so that part is also automated too. And if it is passing that particular test, say gain specification, you do the next test in the sequence until all the tests in the sequence for that particular device runs out. Okay, and when you are done with all the tests and say you found that the circuit is meeting the specification, you declare the circuit is good. So you call it a good device or acceptable device, and that has to be binned out. Okay. So after you binned out, you repeat this step 5, which is basically placing the part on the contactor down to the binning for the next device, and you do so on and so forth. When you run out of the devices on a single strip, you load another strip to test it. Okay. So basically this entire thing kind of gives you the background of what happens in production tests. Now we go about the actual care abouts that are involved in RF circuit testing. Okay, so like I mentioned that it is, I mean, a test list or a sequence of tests contains multiple specifications to measure. Okay, so here I am showing a typical series of tests or series of specifications one would have to exercise for qualifying that device to be good or faulty. Okay, so you would be doing your deep diagnostics first. Basically, you have to make sure one time that whatever test fixture you have got is working fine or not. Okay, after you will do the continuity and adjacent pin short test. What it means is that suppose you have put the device in the contactor and the contact is not good, so it may appear as an open circuit. So before applying say RF signal, it's no point, I mean if the contact is not good, it's no point going running your battery of RF tests. You first should better check the continuity, right? So adjacent, okay, there is another aspect of the continuity test, by the way. When we are talking about package level testing, in the wire bonder, sometimes what happens is that when the die is getting attached to the so-called the die attach, and you are bonding out the die pad to the package pin, it sometimes runs out of that bonding material, wire bonding material. So it happens that say you in this case the wire bonder started from this location, it bonded out all of them, and suppose the bonding material or the gold bonding material that it is using to connect the die pad to the package pin, that particular material has run out. So what will happen is that it will appear as an open circuit. So there will be no connectivity between the die pad and the package pin. Okay, so you have to catch that also, right? And another thing is that during the wire bonding process, what can happen is that there may be crisscross of the wire bonding. So the two adjacent pins may appear as a short circuit. So in this line, when you show continuity and adjacent pin short test, we are making sure that there is no crisscross or there is no short circuit between two adjacent pins. Then there are IO leakage check. Actually, one thing interesting is that although this is purely a DC level test, in terms of high speed testing and RF testing, it is also crucial. The reason is that, for example, say you have that 1.5 gigahertz, let's say 1.5 gigahertz RF output VCO. Sorry, RF output from the VCO, PLL VCO synthesizer. Okay. Now, if there is any leakage within the RF output buffer, what could happen? It runs well up to say 1.3 gigahertz, and the magnitude or peak-to-peak swing of the waveform is gradually degrading as you move the frequency up, because there is a current path or leakage current path which is stealing the current away from the RF output buffer. Okay, so although it looks like mundane DC tests, these kind of tests are also crucial before we do any kind of exotic RF tests or RF measurement. We have to make sure that there is no leakage in the circuitry that we are testing for RF performance. Okay. Next is IOP in DC level tests. This is also of the same importance as IOP in leakage tests, like I mentioned, as far as the RF circuitry is concerned. So if at the DC level, if the output swing is not expected, is deviating quite a bit, it's most likely that at high frequency, it is also going to deviate. Okay, so instead of spending so much time for complex RF tests, we can just quickly screen that problematic device out by a small or a short, just DC level test. Okay. Next, particularly for RF circuitry, there is invariably going to be internal low dropout regulator, LDO regulator, so that we make the RF circuitry immune to the VCC variation. Okay, so you should be testing for the internal LDO regulator as well. Similarly for ICC, which is the device quiescent current, device power down current. Okay, all of them have the same importance. These ICC measurements, all of them have same importance with respect to the RF test as the IO pin leakage test. Okay, so if the internal circuit node is leaking because of some process variation or some bridging fault, okay, bridging between two circuit nodes, resistive bridging. In that case, there will be an increase in the leakage, and it's most likely it's going to not run at a higher frequency. Okay, so device power down current test is also a good indicator of RF frequency performance. Okay. Then, if your device is programmable, you have to test for register access, meaning you have to write the values, read back. These are I mean, fairly straightforward things. Then digital scan, digital based, etc. But I'm not going to read out everything. What we'll be concentrating on is that these last three sections. Okay. If you have some RF embedded circuitry or RF output circuitry or RF input circuitry, you have to check for frequency coverage. So you have to check for the frequency coverage tests in the production test, and if there is frequency feedback meaning if there is any kind of PLL device. Let's talk about, say, your mobile phone circuitry. There is invariably PLL VCO synthesizer within it. So you can check for the performance PLL VCO in open loop as well as in a closed loop. Okay. So you have to check for the frequency range compatibility in open loop and closed loop as well. And the third one is the RF power related spectral tests. There are various kinds of RF spectral tests. I'll show at least a few of them in subsequent slides. But before I show them, let me quickly go over what kind of instrumentation that you would see in ATE or automated test equipment. I'm assuming that you are pretty much familiar with the bench equipment like spectrum analyzer or RF signal source. Okay, so I'm not going to discuss the bench counterpart. I'm going to discuss what is there in the automated test equipment. So, like I mentioned, in case of amplifier, okay, you have to apply RF test signal, right? And you have to capture the RF test response waveform. So you have to have a signal generator, RF signal generator within the ATE. So I took the catalyst ATE from Teradyne as an example. So here it is showing the RF signal capture waveform path. Okay, so here you have the device interface board. Okay, and there is so-called the microwave port, which is basically a connection network of RF relays within the ATE itself, which determines whether you are selecting, say, input A versus output A versus output B, so on and so forth. Okay, and it eventually goes to the mixer circuitry. Mixer circuitry, what it does is it down converts the RF frequency down to a low IF frequency. So if you are having, say, 1.5 gigahertz, for example, coming out from the DIB, going through the RF switchyard of microwave port, it's coming all the way down to the microwave receiver input. So this RF signal that we are showing here, you have 1.5 gigahertz going in, okay, and you program the LO so that you get some frequency which you can digitize for data analysis purpose. So here you'd like to program an LO signal or local oscillator signal which brings down the frequency down to, say, 100 megahertz or 50 megahertz, which is good for digitizing and running all kind of frequency domain analysis like FFT and peak search and so on and so forth. Okay, so By the way, this microwave port, microwave measurement module, very high frequency digitizer, microwave receiver, all of these are specific to the Catalyst AT, but I mean the names are going to be different in different platform. In case of bench environment, you are not going to have these names, you will have the entire thing in a single box called the spectrum analyzer. Okay, but in case of AT, there are fine level of control, which or fine level of programmability, using which you can do various kind of data analysis on the RF signal. Okay. So this is essentially a receiver path in the AT RF signal receiver path. Similarly, to apply the test stimulus, we must have test generator or signal generator built in within the mainframe. Again, let us not get bogged down about I mean with the microwave port, microwave source, VHF, AWG, all these names. These are basically various instrumentation names that are present within the mainframe. The basic idea is that the test equipment within the mainframe should have the capability of taking a baseband signal, up converting it, frequency up converting it to RF frequency. Say if I am testing 1.5 gigahertz amplifier, I have the ability to take a sine wave, take it to the 1.5 gigahertz and apply to the dot. Okay, so this entire block diagram is actually showing this what you can do part by part, and this block diagram is not just showing the ability to apply sine waves. You can combine the sine waves. Say you are doing tests for the IIP3 or so-called the input intercept 0.3. I mean IP3 or third order intercept. In that case, you must have multiple sine waves, right? So you have the power to, or you have the ability to combine multiple sine waves. Suppose instead of an LNA, if you have say some transceiver meaning transmitter and receiver, say some Bluetooth module or some GSM chip IC which goes in a cell phone. So you need to have data stream modulated at say 1.9 gigahertz, right? So the AT would have the capability to modulate a data frame or to modulate data signal in the baseband at low frequency and up convert in the frequency, apply it at 1.9 gigahertz to apply the test waveform. So all these instrumentation are there within the AT. Okay, actually these are the things that make the AT so costly, because all of them are not only there, but they are very much programmable using high level programming, C-like or Pascal-like program. Okay, even the latest and greatest technology that has come up from Teradyne for say in this particular diagram I am mentioning Catalyst RF, right? There are platforms like Teradyne Ultraflex, which is the latest and greatest from this particular vendor, again costing millions of dollars. But all of them, the whole purpose is to make the whole things programmable, as well as programmable from the high level. Okay, not just say connect some switch or disconnect some switch, something like that. You can use C-like language to program it to sequence all the RF tests. Okay, so that is the hardware side. Okay, now what I'm going to do is that I'm going to discuss at least a few specifications that are used or that are that come most frequently for RF circuitry. Okay, so first one would probably be the output power. Okay, in the PLL VCO synthesizer example, what you saw is that at 2.1 gigahertz we have minus 5 dBm power. This is essentially the output power specification. Okay, input to output gain, noise figure meaning how much noise that particular circuitry is adding on its own to the output waveform. Nonlinearity specification. Nonlinearity specification as in, like if you have a perfectly linear amplifier, if you increase the input signal swing, your output signal swing is just a constant multiplied with the input signal waveform. But in RF it doesn't happen like that, right? It goes quickly into the saturating region. So your gain is going to gradually compress. So you have to characterize it, you have to test for it in production test. So nonlinearity specifications like gain, compression and third order intercept will come in picture. At least for the first few over here, I am going to go through in the subsequent slides. Next is the input frequency selectivity. Suppose I have some amplifier meant for say GSM application, which is say centered around 1.9 gigahertz, for example. So it should not work at 2 gigahertz, it should not work at 1.7 gigahertz. So we are talking about a selective range of frequency for operation. So suppose I have a signal applied at 2 gigahertz. Is it able to reject the signal? Is the dot able to reject the signal? Dot meaning device under test or not? So that will be given by the frequency selectivity signal. Similarly, the GSM transceiver, in the GSM transceiver, suppose I have the transmitter side, okay, it is giving out power centered around say 1.9 gigahertz. It should not give out power at 2 gigahertz, it should not give out power at 1.7 gigahertz. So the question is, when I activate the RF output of that particular GSM transmitter IC, is it giving any output power at 2 gigahertz or is it giving any output power at 1.8 gigahertz or 1.7? So that you have to check. So that comes under output spectral mask test. Okay. Next one is frequency harmonics. Probably this one is the most that we encounter first as we study electronics. So every frequency that will come out of the RF output or some RF block, output of the RF block, will go through nonlinearity. So there will be odd harmonics as well as even harmonics. Okay. So there would be specifications saying what is the maximum amount of harmonics that can be there, that can be present at the RF output compared to the carrier frequency. For example, say this amplifier say is operating at 1.5 gigahertz. Now at 3 gigahertz you have one component, right? At 4.5 gigahertz you have another component. So if the specification says that the harmonic has to be at least 20 dBc, 20 dBc means 20 dB down from the carrier. Okay, whatever the carrier amplitude would be, it has to be 20 dB down from the RF output level. So we have to check at 3 gigahertz what is the power level that is coming out, okay, and compare that value with the output power that is coming at 1.5 gigahertz and find out what is the DVC value or dV with respect to the carrier value that you have got for the harmonics. Okay, like harmonics, there can be other tones present at the RF output power which are not harmonically related to the carrier frequency. So suppose the output frequency is 1.5 gigahertz, there may be some signal sitting at 1.7 gigahertz. It is not harmonically related to 1.5 gigahertz. So those are spurious tones. Okay, in short we call them sparse. Okay, so we have to measure for that and test for it. If it says that maximum amount of spar that can happen of a transmitter output is a 30 dBc, it means that all the spurious tones that is coming out of the RF output must be 30 dB or higher below from the carrier frequency power level. The next one is the short-term frequency stability. Short-term frequency stability is applicable for, say, RF signal synthesizer kind of scenario or oscillator kind of scenario. So suppose the RF output frequency is 1.5 gigahertz. Actually, it doesn't stay 1.5 gigahertz. Actually, if you are able to, say, sample that waveform, run a FFT on it, you would see that you are not getting just one tone at 1.5 gigahertz. There is a finite amount of power that gets spilled from 1.5 gigahertz over to the adjacent frequency. So that is the short-term frequency stability, okay, or so-called the phase noise of that oscillator running at 1.5 gigahertz. Okay, so that can be another specification for the RF circuitry. Next one is frequency pushing, also frequency pulling. Frequency pushing meaning, I mean, these two also apply for the oscillator or synthesizer kind of scenario. Frequency pushing means that if you vary the VCC value of the IC, ideally the 1.5 gigahertz, suppose that is the expected frequency that is coming out, it should not move around. But if the circuitry is sensitive to the VCC, when you vary the VCC, there may be delta amount, maybe 1 kilohertz or 2 kilohertz variation on that 1.5 gigahertz. So 1.5 gigahertz plus 1 kilohertz. So frequency pushing is that delta, frequency delta with respect to the VCC difference. So that is another crucial specification for synthesizers, RF synthesizers. Okay. Similarly, frequency pooling. Frequency pooling means that suppose that 1.5 gigahertz is coming out of that synthesizer. Okay. Now, assume that that synthesizer is designed for 50 ohm, so that it is matched with the, say, 50 ohm environment. Now, if you have, say, 100 ohm load instead of 50 ohm, the question is, will the frequency stay at 1.5 gigahertz or will it move around? So the frequency pooling is the delta variation in the frequency of RF synthesizer or RF oscillator with respect to the load impedance variation. Okay. Next set of things, modulation domain specifications are RF specifications, but that has got something to do with the baseband waveform. What we mean is that when we are testing for, say, let's say GSM transmitter and receiver, so there is certain digital modulation scheme and demodulation scheme is going on in the baseband, right? Okay, and suppose it is using the, not suppose, actually GSM transceivers uses the GMSK or Gaussian mean shift, minimal shift keying modulation and demodulation technique. Gaussian minimum shift keying, actually, GMSK. So here, if you have to measure the modulation domain specification at the RF transmitter output, what you have to do, you have to capture the RF signal, pass it through a receiver, demodulate the data in the baseband, and see whether the quality of modulation degraded when it went through the transmitter RF front end, right? So things like error vector magnitude error, phase error, modulation signal to noise ratio, input modulation input sensitivity, these are the things that are to do with the modulation domain specification. Okay. Other than these specifications, meaning spectral domain specifications and modulation domain specification, we have general purpose or general signal integrity specifications that applies to anything irrespective of the circuitry, like voltage standing wave ratio, right? Time domain reflectometry. So if the system is designed for 50 ohm and some component is not 50 ohm, it's sitting at, say, 60 ohm, right? So there will be some reflections going on. Using time domain reflectometry or VSWR measurement, you can figure out where the problem is in terms of impedance matching. Okay. Similarly, S parameters, reflection coefficient, all are to do with the signal integrity. Okay. And other circuit specifications which are also there, but they are not necessarily spectral specifications or modulation domain specifications, like the ICC consumption or the quiescent current consumption and the power consumption, corresponding power consumption within the IC. Okay, that is not really frequency domain, but that has got something to tell with the circuit specification. Similarly, if you have, say, power amplifier, RF power amplifier within your RF system that you are testing or measuring the RF performance of, your power amplifier performance efficiency or output efficiency, that can be also a specification. Okay, so these are the a gist of circuit specifications. Okay, in the beginning of the discussion or beginning of this lecture, I mentioned that we're kind of going to give introduction. Some of the terms may be unfamiliar to you, but you can always refer to the textbook or material, or if you are going to do research on RF circuit design or RF testability later on, you would find this information useful. So even if some of the terms that are not familiar to you, I would say just listen through it, and let's move with the presentation. So we go through actually I kind of mentioned each specification, at least the spectral specification in short. So gain and third order intercept are shown over here. So in case of third order intercept, what we are interested in measuring is that the intermodulation distortion component or the IMD component, because of the nonlinearity of the RF block. The way we test it is that we apply two frequencies to the RF block. It could be amplifier, it could be mixer, or it could be some other RF blocks, a passive filter. Okay, so we apply two RF frequencies, and if the circuitry is perfectly linear, we should just expect F1 and F2 if it is an amplifier, right? But if the circuit is nonlinear, there will be an intermodulation between F1 and F2, and there will be other tones as well. So what third order intercept does is that it measures the amount of non-linearity appearing in the form of this IMD frequency or IMD tone. So if there is a specification which says that your third order intercept has to be, say, 30 dBc, it means that whatever power value that you measure, actually 30 dBc is really too good for RF circuitry. Let's say if it is 15 dBc, so it means that whatever power level that you measure at the output, the linear component, compared to that, this IMD tone or intermodulation distortion tone has to be 15 dB or higher, lower from the linear component value or linear component power level. Okay. Second, in this one, I'm trying to show what I discussed as spectral mask test. So let's say our GSM transmitter is giving out power at 1.9 gigahertz, centered around 1.9 gigahertz. So in the adjacent channel, the power level that is getting spilled over from the main channel, that must be lower than certain dBc, which will be given as a specification for the RF design. Okay. So this is one spectral mask test. So in case of this test, you are sending out a modulated waveform into your RF circuitry. You are getting modulated upconverted output at the RF frequency, and you are looking at the spectral purity of the RF output. Okay. This is the noise figure measurement arrangement. In case of noise figure, how much noise this RF block contributes on its own, there is so-called the Y factor method that is popularly used, to measure the noise factor or the noise figure. So here we have a noise source. In one case we turn it off and measure the power level here. In another case we turn it on, this excess noise source on, measure the power level here in the spectrum analyzer, and from these two values you calculate the noise figure, basically the noise contribution of the RF block. Okay. Here I am showing kind of using a block diagram what is a short term frequency stability or the phase noise. So if this frequency is 1.5 gigahertz, let's say for that RF synthesizer, if it is ideal output, ideal RF output, we would not see this kind of sloping power spectrum coming out of the RF output. We would just see one spectral line, just single spectral line. But because of the noise present in the circuitry, you would get noise spilled over from the main carrier frequency to the adjacent area frequency region, and you get this kind of noise profile. So this noise profile is called so-called the phase noise profile. It characterizes, or it is an estimate for the short-term frequency stability of that RF signal. Okay. Here, okay, one other thing to mention is that the appearance of frequency tones as spurious tones. This is not harmonically related to this frequency. Okay, so this is a spur appearing on the RF output spectrum. Here, again, I'm showing the harmonics and spurs. So if this is the carrier, this is a 2F carrier, 2 times the carrier frequency, 3 times the carrier frequency over here. So all of these would be specified at the RF output. Okay, and here, in addition to the RF frequency output harmonics, I'm showing the spurious tones. Okay. And like I mentioned, for frequency pushing, suppose I was getting a frequency RF frequency output at 1.5 gigahertz. I do not do anything to the circuitry except I change the VCC. The RF frequency location can move from the 1.5 gigahertz. That delta frequency is the frequency pushing amount or frequency push amount. The unit is usually hertz divided by the delta V, which is hertz divided by V. Okay. In case of frequency pooling, we just change the load for a particular load condition, say from 50 ohm to 100 ohm, and we see where the frequency content moved from 1.5 gigahertz. In this case, the unit is hertz, just hertz. Okay. Now, from this point on, what I am going to consider is that to measure a specification on the RF output, what are the different approaches that are existing that you're going to use in the bench as well as in the automated test environment. Okay, so there are several approaches for measuring our RF output power. Some are frequency sensitive, some are broadband. Okay, I'm going to go through a few of them. So the very first one, which is there in the which is present in the spectrum analyzer that you use in the bench environment, is the swept-tuned spectrum analyzer, which is the most common method that is used nowadays in case of spectrum analyzer. What the basic advantage it gives is that you can go very high up in the frequency in terms of measurement. Okay, there is another type of frequency spectrum analyzer, which is the FFT-based spectrum analyzer, but the performance is not so good of that. The main reason is that the input bandwidth of such spectrum analyzers are not that good compared to the spectrum analyzer, swept tuned spectrum analyzer. Actually, you know that in terms of circuit design, there is a trade-off between gain and bandwidth, right? If you increase the gain, you cannot increase the bandwidth much. In case of sampling based spectrum analyzer or FFT based analyzer, where you are sampling the waveform, incoming waveform, and then taking the FFT, your bandwidth requirement starts from DC all the way to at least two times the sampling frequency, right? The Nyquist frequency. But in this case, the bandwidth on the front end is really narrow. You can take a bandpass filter and just select say 1.5 gigahertz plus minus 1 megahertz as your bandwidth. You don't have to go from the DC to all the way to 1.5 gigahertz. Okay. So this is a swept tuned spectrum analyzer block diagram. So you have input attenuator, basically RF output from the DUT or device under test comes in, goes to the input attenuator, that is for accommodating a high amount of input dynamic range. What is input dynamic range? Input dynamic range is the lowest level of power level that you can measure to the highest level of power level that you can measure, right? So if the input dynamic range says that it's 10 dBm, the maximum output power that can go in the front end of the instrumentation is 10 dBm, right? But when you are programming the measurement for spectrum analyzer at 10 dBm, what you lose on is the resolution. So basically, I mean, there are trade-offs, but let's just concentrate on the basic mechanism that is used in spectrum analyzer, which uses swept tuned mechanism to capture the RF spectrum. Okay. So there is an input attenuator to accommodate for the input dynamic range. Then there is bandpass filter to band limit the signal. This is really the down conversion unit, the down conversion mixer. It goes to the resolution bandwidth waveform. I believe that most of it is familiar to you as you have used the spectrum analyzer. Now, from that point on, it goes to the DSP domain. DSP domain meaning you have the programmable gain, you have the amplifier, you have the detection of the spectral envelope, then you digitize it and see it in the display. So basically, suppose I have to measure a test response at 1.5 gigahertz plus minus 1 megahertz, what I would do, okay, I would program the sweep generator over here, starting from 1.5 gigahertz minus 1 megahertz to 1.5 gigahertz plus 1 megahertz. So it will sweep from low frequency to high frequency, and this resolution bandwidth is basically the precision in terms of the frequency selectivity. So if I say that the resolution bandwidth is say 3 kilohertz, so it takes the signal 1.5 gigahertz signal, passes it through the filter, so you get a very sharp say 3 kilohertz peak out of it, and that peak is swept from 1.5 gigahertz minus 1 megahertz to 1.5 gigahertz plus 1 megahertz, right? Because that is a sweep generator. So that is swept and that comes to the baseband, and we do the processing and finally we display it. Okay. So this is basically the working principle of the swept tuned spectrum analyzer, which you can use to measure the RF output power. Okay. So essentially the waveform that you get in the baseband, actually the spectral display that you get, this peak will be related to the entire, to the RF output waveform that is coming in through the entire down conversion gain in the process. So if you know the waveform over here, you multiply the gain, conversion gain, you get the output power of the RF waveform, right? There is another method that you can use for measuring the RF power, that is the network analyzer method. In case of network analyzer method, here you apply also an input, RF input. So basically you are sweeping the input spectrum of the RF waveform, and for every frequency in the frequency sweep, you are measuring the RF output response. Okay, so actually probably I'm not going to go through the detail. I see that it's becoming more and more complex. So basically the basic principle is that in case of network analyzer, you apply a stimulus. So your input frequency is known. In case of spectrum analyzer, you are sort of searching for the RF output waveform. So RF output waveform that this instrument sees is not synchronized with the waveform that is coming in. Whereas in case of network analyzer, since we are applying the RF waveform, the output and input are always synchronized because we know the frequency upfront, what frequency that we are applying. So it actually takes a lot of complexity out of the measurement hardware or the measurement instrumentation. Okay. Now both of them are spectrum sensitive, meaning you not only get the power level information, but also you get the frequency information, how your RF output power level spreads from say 1.5 gigahertz to 1.7 gigahertz, right? So you have two things, two components coming out of the measurement unit, measurement instrumentation. Okay, one is frequency, another is RF output power. But there is another method which is the broadband method, also called the RF detector method, in which what you do, actually I'll show that, actually I don't have the slide over here, let me describe. What you do is you have detector like say diode detector, or you have detector like transistor amplifier detector, to square the waveform and take a root of it. I mean take average of it and take a root of it. So basically it's RMS detector. Okay, so there are detectors like peak detector. You see all of these RMS detector, peak detector that you have probably encountered for low speed analog circuitry. The only challenge is that in case of RF circuitry, how we achieve the same functionality for wide bandwidth and achieving a good dynamic range, because RF circuitry will not be very much linear. Okay, so in that case, what we do, what we can do is that the peak detector or whatever the RMS detector that we design, we can plug in within the circuit itself. So here I am showing a block diagram of a transmitter. You have a digital modulation generator within the DSP. Okay, you have D2A converting that digitally modulated waveform into analog. So we have a low IF frequency over here. Okay, then you are band pass filtering it. So we have a band limited signal. You have the mixer. LO is being provided by the VCO. So if the VCO is say 1.9 gigahertz, it will take the low frequency baseband waveform or low IF waveform and frequency up convert it to the 1.5 gigahertz around it, right? So that is the basic principle of the mixer. And then you boost the power level of the RF signal using power amplifier, send it through the diplexer. The idea of diplexer is that in case of transmitter and receiver, let's say your cell phone, your transmitter and receiver are working simultaneously when you are talking, right? So if the cell phone circuitry, the front end, is working at say 1.9 gigahertz, both the transmitter and receiver exactly at the same frequency, then the power level, since the power level of the RF output circuitry from the transmitter side is so high, it is going to swamp or it is going to overpower the receiver side. So what it is usually done is that the output frequency of the transmitter is slightly offset from the receiver side. Okay. So the circuitry that is used to multiplex in the frequency domain is called the diplexer. So if it is say at 1.9 gigahertz plus say 200 kilohertz, see this is probably running at 1.5 gigahertz, sorry 1.9 gigahertz minus an integer multiple of 200 kilohertz or something. So that these are frequency multiplexed. Okay. Actually, because of the time limitation, what I'm going to do is I'm trying to wrap up everything very quickly. This is one particular circuitry that is used as the RMS detector circuitry, where you can, if you can feed in the RF circuitry within it, you get a DC level corresponding to the output power level of the RF, right? Okay. And there are certain limitations. Let me not go into the detail of how it works. There are certain limitations in terms of frequency sensitivity, because it's a broadband circuitry. There is a certain limitation in terms of input dynamic range, how much power level can it handle the input, and also the lowest amount of power level that you can feed in the input. But the biggest advantage is that unlike using the spectrum analyzer or network analyzer, you can put the small circuitry within the circuit under test itself, so that you can measure the power in situ or within the circuitry under test. So the main challenges of the design for test, like this one, this is a design for test. We are designing a circuitry to measure certain specification, which is RF output power from the circuitry. Is the additional die area it will take. There is a question, well, we are putting a circuitry within the die, so who is going to test the test circuitry itself, right? So addition of the circuitry can change or can affect the performance of the original circuitry itself. So there is a challenge too. So, and the last but not the least is that requirement of calibration. In case of bench environment or a T environment, you can always calibrate the instrument, but in case of circuitry embedded within the device itself, the device under test, it is very difficult to calibrate it. So probably you can take a look of itself. This one, there are certain things that are crucial for RF measurement and design for test. I'm not going to go through the detail of it, but each of it is an item based upon which the vendors, equipment vendors like Agilent or Advantest or Rosen Swartz, they are researching on it and trying to make the RF measurement capability better and better. Okay, same goes with the test vendors like Advantest or Teradyne. Okay, so there are several terms that we have used. Here is a short list of it. You can take a look at later on. And for this presentation, I have taken the material from this. So if you have questions, you can always go and take a look. And some of them are very, very informative, particularly the number 1 reference, which is a Bible for test and measurement, I would say. And fifth one is also, I mean, if you're doing your research or doing your lab experiment in RF measurement, in that case, this is a very crucial document that you can take a look at. Okay, so I guess we are over time, so I'll conclude over here, and I can take any questions that you have at this point. Otherwise, we'll break. Okay, so we'll break.